Now children, as you have studied the concept of electric potential due to charge, I have another term to introduce to you, and that is potential gradient. Now recall what you have studied in class 11 in properties of matter, a term called pressure gradient. You have also studied a term called temperature gradient. So it is fall in temperature, change in temperature per unit length, or change in pressure per unit length. Similarly, we have a term here, potential, and we'll talk about potential gradient. It is fall in potential per unit length. To understand this, let me first assume we have a charge Q. It's a very simple expression, but it will take you to another level of understanding. You have a charge Q, and at a distance r from here, we have a point, say Q, and then at a distance dr further, we have a point, say P. If I ask, let me assume the kind of potential we will get over here. Maybe at point P, the potential which exists is V. Now at point Q, the potential will be higher than V or less than V. So my concept is, it is going to be higher than V. V plus dV, because it is closer, 1 by 4 pi epsilon naught Q by R. So potential at P is what? V, and potential at Q is what? V plus dV. Now I am assuming a situation, let 1 coulomb of charge, or maybe Q coulomb of charge, is shifted, moved from P to Q. So now I have a charge of 1 coulomb which was kept at P. So at P, if I say you are keeping a charge of 1 coulomb, what force will act on it? Your answer is, it will experience a force that is 1E. So force by system will be how much there? 1E. And it is that force which will keep this 1 coulomb, which will try to move this 1 coulomb away from it. But what we are willing is, we wish to bring this 1 coulomb from P to Q. Now what external force will be needed? If I want to bring this charge of 1 coulomb from P to Q, what external force will be needed? So our answer is minus 1E. So that 1 coulomb of charge was needed to be brought from P to Q. The external force which is needed in order to balance it and then slowly move it inward, P to Q, will be what? Minus 1E. And then if I say, what work is required to move this unit charge from P to Q? What work is required to move this unit charge from P to Q? I can express this work done to move this unit charge from P to Q as external work dot displacement. Let me call this displacement as dr vector. This is dr vector. Force is also in this direction. And it can also be said as Q into VQ minus VP. Now external force is what? Minus E. dr is also in the same direction. Charge is 1 coulomb. VQ is what? V plus dV. VP is what? V. So we are getting minus E dr cos 0 as dV. And we are getting that relation, E is equal to minus dV by dr. Now here dV is what? Here dV is potential gradient. Potential, fall in potential, and dr is what? The separation. So fall of potential or change of potential per unit length is what? Electric field. So this is that important relation which we were looking for. Electric field is equal to negative of potential gradient here. So very important expression we have learned here. Electric field is negative of potential gradient. Now continuing with that information that electric field is negative of potential gradient. If I say unit of electric field is actually Newton per Coulomb, but can we say unit of electric field is volt per meter? So we can also call it volt per meter. Now another important term we are going to discuss here, and that is equipotential surfaces. Now as their names are suggesting, it's about surface with equal potential. So a surface with equal potential should be called as equipotential surface. Now let's assume I have a charge Q, and due to this charge Q we have electric field obviously going radially outward. But I am interested not only in electric lines of force, we are interested here in equipotential surfaces. So just imagine that I have a point charge, my hand is like a point charge, and then I am assuming equipotential surface. So if I go r distance here, r distance here, r distance here, r distance down or r distance back. So I should assume not a circle, instead I should assume a sphere of radius r. So if we assume a sphere of radius r, at every point of this sphere there will be same potential. I will call that equipotential surface. So again I am repeating, a sphere of radius r around it will be equipotential surface at every point of which the potential will be same. It may be carrying a potential, say I call it V1. Now this is not the only equipotential surface that you can have. You can assume another sphere of radius, say R2. So if you are assuming another sphere of radius R2, it is going to be another equipotential surface. And these are not the two only equipotential surface you can have. You can have another sphere of radius R3. That will be another equipotential surface V3. So every next sphere around this point charge would be an equipotential surface. And the point to understand is that at every point of this equipotential surface, the potential will have the same value, and that is V1. Everywhere the potential will be having the same value, that is V1. Similarly, at this surface, at this sphere, every point will have the same potential, and that will have a value, say V2. Similarly, at every point of this sphere, the potential will have the same value, and that is, say, V3. So equipotential surface is a surface at every point of which the potential is same everywhere. Now, one thing I can naturally understand from here, and that is the equipotential surfaces are normal to electric lines of force. So equipotential surfaces are normal to electric lines of force. Two things I haven't taken care here. One is potential is same on one equipotential surface, but between two consecutive equipotential surface, yes, obviously there is a potential difference. Second, that electric lines of force are normal to equipotential surfaces. Now this is equipotential surface due to a point charge. Now I have another options, because we have also learned drawing electric lines of force due to combination of charge. So other option is, just imagine you have a charge positive plus Q and a charge minus Q. How the electric lines of force would be? They start from positive charge, they start or end normally to the conductor, and otherwise it is radial here, and otherwise it is coming radially inward here. So equipotential surfaces are this way. Electric lines of force are like this in case of what? A positive charge and a negative charge. But I am interested here in equipotential surface. Equipotential surface is normal to electric lines of force. So in this situation, the equipotential surface is like this. I draw it again in this position. Equipotential surface would be like this. So what you can see is that in the central region where electric lines of force are nearly horizontal, equipotential surface is also nearly vertical. But in the region where the electric lines of force are curved, the equipotential surface is also getting curved. And with the radial where the electric lines of force are, it is completely circular or spherical in shape. So this is equipotential surface in case of a positive charge and in case of a negative charge. Next, I take equipotential surface in case of two similar charges. So you have two similar charges, plus Q and plus Q. If you are trying to find electric lines of force here in this farther region, it is like not affected due to the presence of other charge. But in the central region, the electric lines of force would like to repel each other this way. These are electric lines of force. But if I am interested in equipotential surface, the equipotential surface here would be in the outer region, it will be like this, but it is more curved in the central region. So over here in the outer region, it may be okay, normally like sphere, but in the central region, it is more curved. So here, in this case, the equipotential surfaces have this kind of shape. I would like to draw with different colors so as to give you the idea that they are different value equipotential surfaces, like this. So this is kind of equipotential surface in case of like charges, positive, positive, two negative charges, like that. And we have understood, this is very clear, electric lines of force are normal to equipotential surface, and thus if I am giving you the case where you have electric lines of force which are parallel lines, uniform electric field, how the equipotential surface would be? It should be like this. So in case if you have parallel, or in case if you have uniform electric field, the equipotential surfaces are plane equipotential surfaces of this kind. So we have understood the concept of equipotential surface. So if I ask you, what are equipotential surface? So your answer is, equipotential surface are the surfaces at every point of which the potential is same. Draw, my question can be, draw some equipotential surface due to a positive charge and a negative charge combination, or due to combination of two positive charge, or in case of a uniform electric field. So you have these examples. Properties of equipotential surfaces. Properties of equipotential surfaces. Now, first property of equipotential surface is no work is done. We will write these properties and then we will prove it. No work is done in moving between two positions on an equipotential surface. So just imagine you have a charge Q here and you have this as equipotential surface, and then I am taking a point A and I am taking a point B, and I am moving a charge, say from A to B. I am interested in calculating what work is done in moving a charge from A to B. So your answer is VB minus VA. But here VB is what? VA. So work done in moving from A to B will be what? 0. So your answer is no work is done in moving a unit charge, or no work is done in moving a charge between 2 points on an equipotential surface. So this is property number 1. Let's talk of property number 2. And property number 2 will be the electric field is perpendicular to equipotential surface. Now this is something which we have already observed, but we want to prove it. How can we say that electric field is perpendicular to equipotential surface? For that we again assume we have a charge Q, and this is an equipotential surface. And here I am assuming I am taking, say I am taking a charge from A to B. Now here the electric field is somewhere here, where the displacement vector is from A to B, dl. Maybe the angle between electric field and dl vector is theta. We can say work done to move from A to B, unit charge, will be VB minus VA, and it is also remembered as negative of line integral from A to B. Negative of line integral from A to B. Now VB is equal to VA. So negative of line integral from A to B, or E dl cos theta, is what? 0. So I can say E dl cos theta is 0 here, where electric field is not 0. Electric field is existing here, and dl also is not 0. So cos theta is 0. It means theta is what? 90 degree. So we can say electric field is perpendicular to dl vector. So electric field is normal to equipotential surface. This property we have proved here. Another property, third property, no two equipotential surfaces can intersect. Neither they will touch, like electric lines of force, they would not intersect but they can touch. But here no two equipotential surface can neither intersect nor touch. Why? You have one equipotential surface maybe with a value 10 volt, and you have another equipotential surface maybe with a value 30 volt. It means on every point of this line the potential should be how much? 10 volt. And every point on this line the potential should be how much? 30 volt. But what about this point? As per this, it should have a potential of 40 volt, which is not possible, because if it is an equipotential surface, then every point it should have a potential of 10 volt, not somewhere 40 volt. If it is an equipotential surface, then everywhere it should have a potential of 30 volt, not somewhere 40 volt. So two equipotential surface can never intersect. This is another important information. And then case number 4. That is criteria to draw equipotential surfaces. Now what do we mean by that? Criteria to draw equipotential surfaces. So when I say criteria to draw equipotential surfaces, it means I am looking for, I have a charge Q. But question is, in a small distance, say x, how many equipotential surfaces you can draw. So the fact is that every next point you will have a new potential. So in any distance, maybe x, maybe y, maybe r, maybe x, maybe 1 centimeter, maybe 1 millimeter, you can draw infinite equipotential surfaces, infinite spheres of increasing radius. So question is, when we show them as equipotential surface like different spheres consecutively, then what is the criteria? How many spheres should be drawn in a particular gap? So I have this relation which we have just proved, E is equal to minus dV by dr. Now what is dV stand for? dV stand for fall of potential. Let's make dV constant. If we make dV constant, it means I can say E is inversely proportional to 1 minus 1 by dr, and also I can say that we draw equipotential surface so that every next equipotential surface has a certain has a certain change of potential. That means when I will draw equipotential surface, I will draw my first equipotential surface which may have a potential of say 50 volt. I will draw another equipotential surface which should have a potential of 40 volt. I'll draw another equipotential surface which should have a potential of 30 volt. I'll draw another equipotential surface, it should have a potential of 20 volt. So the point is that we draw equipotential surface and everywhere dV is fixed. So criteria to draw equipotential surfaces make dV fixed. That is one point. Then another information which we are getting is electric field is inversely proportional to minus 1 by dr. Now dr is what? This gap. So where the electric field is stronger, the dr will be less, and where the electric field is weaker, the dr will be high. It means equipotential surfaces will be closer where you have a strong electric field, and equipotential surfaces will be farther where you have a weak electric field. So if you have a charge Q and this is the electric field, then obviously where the electric lines of force are closer, you have a stronger electric field. There the equipotential surfaces will be closer. The density will be higher. But as you are going away, when the potential is, reducing, the consecutive equipotential surfaces will be farther. So equipotential surfaces are closer in the region of strong electric field, and equipotential surfaces are weaker, farther in the region of weak electric field. That is the point we should keep in mind. So these are some very important information about the potential gradient and equipotential surfaces which you have learned here. Very small topic, and now I'll talk about numericals on this concept that you have just learned.